Hello and welcome to G Fun Facts Online. Today we are turning our attention to the restless, titanic force that has pounded against our coastlines for billions of years. While humanity has successfully harnessed the wind and the sun, turning gentle breezes and warming rays into the electrons that power our digital lives, the ocean remains the sleeping giant of the renewable energy family. Wave energy, the extraction of power from the surface motion of ocean waves, represents one of the most technically challenging yet promising frontiers in the global quest for a carbon-neutral future. Unlike the sun, which sleeps at night, or the wind, which can be fickle and intermittent, ocean waves offer a dense, persistent, and highly predictable source of power. It is estimated that the theoretically available energy in ocean waves worldwide stands between 2,000 and 4,000 terawatt-hours per year. That is enough to cover a substantial portion of global electricity demand. Yet, despite this colossal potential, wave energy conversion technologies have not yet reached the commercial maturity of solar photovoltaics or wind turbines. We are currently witnessing a pivotal moment in history, a Cambrian explosion of engineering designs where hundreds of different concepts are vying for dominance, each attempting to solve the riddle of how to survive the ocean's fury while efficiently harvesting its power. To understand where this industry is going, we must first look at the physics of the blue pulse. Ocean waves are not merely moving water, they are energy moving through water. They are generated primarily by the wind blowing across the surface of the sea. As the wind rubs against the water, friction transfers energy, creating ripples that grow into chops, and eventually into fully developed swells. The amount of energy a wave carries is determined by its height, or amplitude, and its period, which is the time between two crests. Crucially, the power of a wave is proportional to the square of its height. A wave that is 2 meters high contains 4 times the energy of a wave that is 1 meter high. This exponential relationship is both a blessing and a curse. It means that during storms, the available energy skyrockets, potentially overloading or destroying equipment designed for calmer conditions. Furthermore, waves have the highest energy density of all renewable sources. Solar panels might capture 1 kilowatt per square meter on a sunny day. A wind turbine might intercept a few kilowatts per square meter of swept area. But a powerful ocean wavefront can deliver anywhere from 20 to 70 kilowatts per meter of crest length. A single kilometer of coastline in a high-energy environment like the Atlantic coast of Ireland or the Pacific Northwest of the United States receives hundreds of megawatts of power continuously. Now, let's explore the zoo of technologies designed to capture this power. Unlike the wind industry, which has converged on the 3-bladed horizontal axis turbine as the standard design, the wave energy sector is still fractured. There is no standard wave machine. Instead, we have a diverse zoo of devices. First, we have the Oscillating Water Column, or OWC. This is perhaps the most intellectually elegant of all wave energy concepts because it mimics the action of a blowhole. Structurally, an OWC consists of a hollow chamber that is partially submerged. The bottom is open to the ocean, and the top is sealed but for a small vent containing an air turbine. As a wave approaches and enters the chamber, the internal water level rises. This acts like a piston, compressing the air trapped above it and forcing it out through the vent at high velocity. When the wave recedes, the water level drops, creating a vacuum that sucks air back into the chamber. The genius of the OWC lies in its removal of moving mechanical parts from the water. The only moving part is the turbine, which sits high and dry above the waterline. To handle the airflow changing direction every few seconds, engineers use a self-rectifying turbine, most commonly the Wells turbine, invented in the 1970s. Its blades look like teardrops and spin in the same direction regardless of airflow. Notable examples include the Mutriku Wave Energy Plant in Spain and Ocean Energy in Ireland, with their massive floating OE35 hull. The second category is point absorbers. If you have ever watched a buoy bobbing up and down in the harbor, you have seen the principle of a point absorber. These devices are usually floating structures that absorb energy from all directions. The most common design involves a floating buoy connected to a submerged seabed foundation. As the wave passes, the buoy heaves up and down. This relative motion drives a linear generator or a hydraulic pump. The challenge here is tuning. Just as a child on a swing needs to be pushed at the right moment to go higher, a point absorber needs to move in resonance with the incoming waves. Modern companies like Core Power Ocean use advanced control systems to trick the buoy into reacting as if it were much larger, artificially inducing resonance to multiply the power output. Then we have attenuators, often called the snakes of the sea. These are long, multi-segment floating structures oriented parallel to the wave direction. As the wave runs along the length of the machine, the varying heights of the water cause the joints between the segments to flex. Hydraulic rams inside these joints resist this bending, pumping fluid to generate electricity. The most famous example was the Pelamis project in Portugal. While it eventually failed financially, it proved wave energy could reach the grid. Next are oscillating wave surge converters. While point absorbers focus on the up and down motion, surge converters exploit the horizontal back and forth movement of water particles found in shallower coastal waters. These devices typically look like large paddles or flaps hinged to the seafloor. As a wave approaches, the water surges forward and pulls back, pushing the flap like a pendulum. The wave roller by Finnish company AW Energy is a prime example, sitting on the seabed and swaying invisibly from the shore. We also have overtopping devices, which function like floating hydroelectric dams. They use large arms to funnel waves up a ramp and into a reservoir above sea level. The trapped water is then released back into the sea through turbines. Finally, there are rotating mast devices like the Wello Penguin. These are completely enclosed hulls containing a heavy gyroscope. As the hull rocks with the waves, the internal mass spins, generating power with no external moving parts touching the corrosive salt water. Regardless of the external shape, every device needs a power takeoff, or PTO system, which is the heart of the machine. Hydraulic systems are common for high-force devices, smoothing out the chaotic energy with pressure tanks. Direct drive electrical systems eliminate fluids by using magnets and coils to induce electricity directly from the motion, though they require massive, custom generators. Pneumatic systems use air, acting as a natural gearbox for OWCs. This leads us to the fundamental paradox of wave energy engineering: survival versus efficiency. To generate power, you must catch the wave. But to survive, you must dodge it. A wind turbine can pitch its blades to let a hurricane pass, but a wave device is physically coupled to the medium. Water is 800 times denser than air. A breaking wave hitting a steel structure is like a truck slamming into a wall. Early prototypes were often torn apart. Modern designs now feature storm modes, where they detune or lock down to ensure survival. Beyond physics, the industry faces the economic valley of death. The levelized cost of energy for wave power is currently estimated between $300 and $600 per megawatt hour, far higher than the $80 for offshore wind or $40 for solar. It is too expensive for banks, and too capital-intensive for typical venture capitalists. However, costs are falling as supply chains mature, and governments in the EU and UK are introducing contracts to support early adopters. Environmental impacts are also a consideration. While there are concerns about mooring lines entangling marine life or noise-disturbing mammals, studies from the European Marine Energy Center have shown minimal negative interactions. In fact, wave farms often act as artificial reefs where fishing is prohibited, allowing fish stocks to recover. They also have a low visual impact compared to offshore wind, often sitting invisible from the shore or low on the horizon. As we look at the leaders in the field for 2026, companies like EcoWave Power are succeeding by attaching floaters to existing piers, keeping expensive equipment on land. Core Power Ocean is leading high-efficiency offshore buoys, and Ocean Energy is leveraging shipbuilding scale for their massive platforms. The future of wave energy likely involves the blue economy. Wave power is perfect for desalination, providing fresh water to islands without fossil fuels. It can power remote island grids that currently burn expensive imported diesel. Ultimately, we may see hybrid parks where offshore wind and wave energy coexist, sharing infrastructure and providing a smoother, more reliable power output. Wave energy is no longer just a science project. It is an industry entering its industrialization phase. We are standing on the edge of the ocean, watching a revolution of steel and software fight a battle against the wildest environment on Earth. The waves will never stop crashing, and if we can learn to ride them, we will unlock a power source as eternal as the tides. The sleeping giant is waking up. Thanks for listening to Fun Facts Online.